Hi everyone, it's Dr. Dan, and I just wanted to make a quick video of what we didn't get in lecture today, but what you guys are going to need in order to analyze your instrumentation, your temperature data. So I'm going to just kind of go over the whole thing, even though we did some of it in lecture. That way it's just one complete video of everything you need to do. So the file we're going to analyze is in this lectures area. We're going to look at this example thermistor data.csv file. Right, so this is me taking a thermistor, starting at room temperature and sticking it into a container of freezing water. And so I got the data, downloaded it. It's a CSV file that can be easily opened in Excel. And this is what your data looks like when you open it in Excel. Okay, so this is what your data for all your temperature sensors will look like. You basically have the time in milliseconds and the temperature it's measuring in degrees Celsius. All right, so there's a lot of things we could tell from this. So I'll start off. I'll just make a graph first so we can see what it looks like. I'll make a scatter with just the points. So right, you see this initial point is where I'm just kind of holding it at room temperature. I've started the Arduino, but I haven't dunked the sensor into the freezing water yet. So then I finally dunk it in the freezing water and hold it there for 40 or so seconds. To just kind of see how it measures the temperature of the freezing water over time. All right, so I'm going to delete this for now. But there's a lot of things we can tell from this data that we're already collecting, right? Like we want to be able to evaluate our temperature transducer and along with the signal acquisition circuit. So one of the things that we're always interested in is sampling rate, right? For a digital acquisition system, sampling rate is the most important thing. So we can actually tell the sampling rate here, right? We can look at this data and see that it is sampling about 4 times per second, right? So we can calculate that if we want to. I'm just going to go ahead and insert another column, and I'm going to say like difference in time, right? Something like that. So I'm just going to go ahead and just do this equals the difference between the two. Copy it all the way down, right? I could even up here, I can just calculate an average of this whole column if I really wanted to be, make sure I can see what I'm seeing, but really I can see this is in the 250 range. That is my average milliseconds between each sample. So that's, like I said, 4 samples a second. That is our sampling rate, is 4 hertz. The other thing that we can tell, which is pretty cool, is we can see the resolution of the sensor in temperature, right? So a lot of times you get some resolution information of the sensor in bits, right? Like for instance, we know the Arduino ADC has a 10-bit converter on it. So a lot of times it's hard to understand what that actually means as far as like, okay, the actual physical value. But you can kind of see what's going on here. Like if I do, again, I just do the difference from one measurement to the next. Again, I'll copy this all the way down. Okay, what we kind of see here is where this data is supposedly static, right? You're seeing it change by about 0.09 or, 2 times 0.09, right? So it's not, in other words, it's not changing by 0.04 or 0.03 or 0.07, right? It's only changing by this fixed amount. We can even go down to the bottom here of our data. Okay, and so it's changing by 0.1, 0.2, which is close to 0.09. So our resolution is somewhere in the 0.09 to 0.1 area, right? We're not seeing like 0.15, in other words, right? That would be impossible to have a 0.15 if your resolution is 0.09 to 0.1. Okay, so we can also see the resolution. The other thing we can, just right since we're here at the bottom, right? This may be an okay measure of some sort of accuracy of the measurement, right? Like in freezing water technically should be 0 degrees Celsius. Maybe we didn't have a perfectly frozen water bath that was at 0 degrees. But if you make it right and it's mostly all ice and just some water in there, it should be really close to 0 degrees. So maybe we can get a feel of the accuracy of the sensor too, just by looking at this data. So last thing we want to look at is then a time response, right? So I showed you the graph before. It's not instantaneous, right? It takes time. So how can we calculate that time response? And that's what we're going to spend the rest of the time talking about and what we didn't get to in class. So the one thing we want to notice is we're going to fit this to this exponential curve. All this data that I'm highlighting here above here, like it's all constant, right? So it's not really fitting our exponential curve, for we haven't started cooling it down yet. So I really want to think about, okay, where do I want to start this off? I think I decided that row 17 would be a great place to start us off, because that's where it seems to, okay, now it started dropping. And so what I'm going to do is just kind of remake a graph here with putting time and temperature. And I'm going to do this where I convert to time in seconds, and I'll just put the temperature here. That way when I draw my graph, it's like right next to each other, right? So my time in seconds, what I want this to do is I want this to basically go 0, 0.25, 0.5, 0.75, right? So then when I graph the temperature, we start at 0 time, we go to whatever the end time is, in seconds, not milliseconds. So the way I can do that in Excel is just take the current time and subtract it from the initial time, which happens to be A17 as well in this case, right? But I'm putting dollar signs there because we're not changing that initial time. So that's where we get to 0. Again, I'll divide by 1,000 on this to go from milliseconds to seconds. And if I copy it down, right, so it only copied it there because I had this filled in, so I'll copy it the rest of the way. Right, we're getting or this is the time in seconds starting at 0 from that time step. The temperature is less tricky. We just want it to be the temperature. And the only reason I really copy over the temperature is just so I can then grab these two and make a nice graph, right? So that's what I'll do. Grab these two columns. I'll say insert a chart. Okay, and so we have our place where it's just decreasing. Okay, so we want to calculate the time constant of this. Okay, so the equation I said that we want to fit is our temperature as a function of time is T final plus T initial minus T final times E to the minus T over tau. Right, that's our equation, our model, if you will, right? So I'm going to put that in this column over here beside the temperature. Okay, and so our job is now to translate this, equation into Excel, an Excel equation. So the one thing we're missing are some of these numbers, right? So we're going to want a TF, we're going to want a T0, we're going to want a tau. I think those are the only things we need. I can go ahead and align them over this side just so we can see them a little better. All right, so our question is, where do we get these? The tau is what we're solving for. Okay, that's our thing that we need to find. Right now, like I'm just going to set it at 1, right? Just 1 second is close enough. I will note you can also do this in milliseconds if you want, but then your tau would be in milliseconds as well. So if we didn't divide by 1,000, then I would have to have my tau as 1,000. So but I've done it in seconds, so I'm doing this in seconds. And then T final and T initial. And those are actually easy to see from the data, right? Our T initial is like all this before the temp starts dropping. So we could, we could just take this 1 point and say this is equal to that. I like to take in the experimental error. So I'm going to say this T initial is the average of kind of all these points here. Right, that's our initial temperature. And I'll do the same thing on final, right? I could just take the last point if I wanted. And because it's still kind of going down, I think that 1.39 is probably a pretty good last point to take. If you'd seen it like jumping up and down, maybe you take the average like I did at the start. But I'm just going to set it equal to that last one. Right, so now we have our variables here. T final, T initial. Again, the tau is just a placeholder for right now, but I'm going to type that equation in Excel. So this equals T final. Okay, and I'm going to put some dollar signs around these because when we copy it down, right, we don't want them to change. Plus T initial minus T final. Again, put some dollar signs. All right, times e to something in Excel, that's the exponent function. So I go e exponent minus, and it's t over tau. So my time is just there, divided by my tau, which is F12, which I'm going to also put dollar signs. Okay, and as expected at time equals 0, my T0, it equals my T0, right? So I'm going to go ahead and copy that down. You can already tell that this goes too fast, right? We can see that it's going much faster than my experimental data. So obviously this tau is not correct 1, but I do want to add this to the graph, right? So I'm going to go here, select data. I'm going to add another, so I'll say this is the equation, x values. I want to be my times, my y values. I want to be these temperatures. Okay, so that's where I see that, okay, this is obviously way too fast. I'm going to change this from markers to lines. I'll make that a solid line. I'm going to give it orange. And then markers, I'm going to say no markers. Okay, again, to differentiate the fact that this is an equation, so it's a smooth thing going on, and these are points because it's our data that we've collected. Okay, now it's just a matter of making it fit, right? Just like we did with our diffusion model. I can just increase my tau until I finally make it fit, right? And so somewhere in that 7 or 8 range looks pretty good, right? We can make a conclusion about tau based on that. So that's awesome, right? This temperature sensor has a tau of approximately 7. Now, I'm going to make it a little bit off. It turns out, you know, like it was 7 or 8. That seems kind of, you know, okay, a good guess. And just like our Excel diffusion model, it'd be better if we could do like, hey, I want to know the exact value this is. So in the Excel diffusion model, I just told you to try to get it close. I want to show you a way that we can get this thing to be as good as it can possibly be. In order to do that, we're going to have to use Excel. There's add-ins in Excel that you can add in, and one of them is called the solver. I think it depends on your version of Excel. So there's like add-ins things here. That's not where you want to go. What you want to do is you want to go to File. And again, this might be a little bit harder for those of you who have Mac and don't have the exact same thing, but I think you'll be able to find it. You're looking for the solver add-in, right? So if we go to File and I go to Options, I go to my add-ins. You go to Manage your Excel add-ins. So I'm going to add my solver add-in in here. Oop, not the Euro conversion tools. So I'll hit OK. It takes a sec. But now I have my solver add-in here. It's actually under this data tab. Okay, and so I have over here under analysis, there's solver and data analysis. Okay, so now what we want to do is we want to have a measure of how good this is, right? And so one way of figuring out how good it is just figuring out how far off we are, right? And minimize how far off we are. So if we want to know how far off we are, we can just calculate the error in each measurement, right? And so the error in each one is the difference between the actual experimental value and our value calculated in the equation. Right, so I could copy that down. What you'll notice is it depends on which direction we are. It's like some of these have positive signs and some have negative signs, right? And so what we're interested in is we're interested in the total error. And so normally what happens when you're trying to reduce the total error, it's called a sum of squares, so that you make everything positive by squaring everything, right? So I want instead of just the error being just those subtracting, I'm going to subtract, but I'm going to square. Oops. Let's redo this. Subtract these two, and I'm going to square it. And that way it doesn't matter which order I do the subtraction in. It's always making it a positive value, right? And it's always calculating the error for every single point as a squared value. Now, it's not the actual error, it's a squared error, but who cares, right? If you sum up the actuals or you sum up the squares, like you're still getting you can still get a total. So let's just call this the sum of squares. And so I'm going to just say this is the sum of all of these values. Okay, and so whatever value this is, right, 154 is my sum of squares. You can tell then, if I get further away, like if I type in a 10, my sum of squares increases, which means it's worse, right? It's a worse fit. I can type in 5, okay, it's even worse, right? But as I get closer to 6, 7, 8, right, you can start to see that sum of squares gets smaller and smaller. So it looks like we're down around 7 is about the right value, right? I could even try to do it myself, right? Ooh, that gets even smaller, right? So my goal here is to minimize that sum of squares error, and that will give me the best possible match. Now, that's why I had Solver loaded in here, because Excel can actually do this for me. So I'm going to open up Solver. It's going to say set objective, okay? And you're going to set the objective. You pick a cell, and you can set it to a max, a min, or set it to a value. And so what I want to do is I want to minimize this. Okay, it already had this selected because I had it selected. I want to minimize this cell. Okay, and it's saying, how do you want to change that cell? And I want to change this cell. That's the only one I can change. Okay, so I'm going to have Excel go ahead and try to minimize this by changing my tau value. You could put constraints in here. For this, we don't really need to do constraints. That might be like, hey, we don't want tau to be negative, or we don't want tau to be over 1,000, right? Obviously, we don't want tau to be negative, but it's not going to be. We don't need to worry about that for this, right? So this is all I need to do. Set I-17 to a minimum by changing F12, hit solve, and some magic happens, and it tells us our minimum tau is 7.36, minimizing the sum of squares. And you can either restore the original values or keep the solution. I'm going to keep the solution, right? And so this is my best guess at what the tau is for this temperature sensor. All right, that's how you do it. So that's why Excel is really, really cool. You can use Solver to do some of these things. You guys will do this for all your other temperature sensors as well. You will figure out the tau value for all your other temperature measurements using this same technique.